Thank you so much for the invitation and for the introduction. Um, okay. Okay, so my talk today is titled Black Hole Dynamics at Large D. And first, a disclaimer. This is a talk on a subject that I worked actively on a few years ago, in the period 2015 to 2018. I have not thought actively about since. So this is a review talk, and every result presented here is 3 years older or more. Okay. With that disclaimer out of the way, this talk is based largely on work done by two groups. The first of these two groups is the group of Emperan, Suzuki, Tanabe, and collaborators, whose principal papers I've listed here. Okay. The second is the group in India, including my colleagues, my postdocs, my students, and myself. And the papers are listed here. My references in the main body of the talk will be a bit sloppy. I apologize for that. Okay. So as all of you know, black holes are fascinating objects that undergo rich and complex dynamics. Of course, the world has many fascinating objects that undergo rich and complex dynamics. But a remarkable thing about black holes, as opposed to other such objects, for instance, as opposed to supernovae, is that the dynamics of the system is governed by a magnificently simple and precisely known and very easy to write down equation. And that equation is simply Einstein's equation in a vacuum, namely Rmn is equal to 0. So despite the simplicity of the apparent simplicity of this equation, the ease with which we can write down this equation, the dynamics of black holes in nonlinear regimes is very poorly understood. Okay. Often when we want to understand something interesting like two black holes colliding, the only recourse that we have really is to move to a computer, which has its own issues, and this whole state of affairs feels somewhat unsatisfactory. Okay, so when faced with an interesting but apparently intractable problem, one strategy for progress is to enlarge the problem and introduce a sort of natural parameter into a problem which may not have had the parameter in the first place. In this talk, I'm going to try to make progress on trying to understand black hole dynamics by introducing a new parameter into the problem. And the parameter that will be of interest to the bulk of this talk is 1 over d, where d is the number of spacetime dimensions. As a warm-up to this story, however, I will first recall an older, and it will turn out related story, namely the fluid gravity correspondence. Okay, so once again, fluid gravity can be motivated by the desire to try to understand black hole dynamics in some regime in an analytically interesting way. Okay. So the idea here is, instead of one way of saying it is that the idea here might be, instead of generalizing the vacuum Einstein equations to large D, as we will do later in this talk, we generalize the vacuum Einstein equations to vacuum Einstein equations in ADS space, namely vacuum Einstein equations with a negative cosmological constant. So this equation. Now, just like the vacuum equations, Einstein equations in flat space, these equations admit black hole solutions. And the simplest of these solutions are just spherically symmetric, stationary, static black holes that sit somewhere in ADS. When these black holes are very small, they become basically identical to black holes in flat space. So studying them doesn't buy you anything. You've gone back to the problem that you were interested in the first place. However, when these black holes become very large in units of the ADS radius, in units of this RADS here, they become very different from black holes in flat space. And one might wonder, perhaps there is some simplicity, something to be gained by studying black hole dynamics in the limit where these black holes become very large in units of RADS. Indeed, the limit RH, where RH is the event horizon radius, divided by ADS goes to infinity, together with a coordinate transformation, coordinate redefinition, is completely well defined. And it essentially turns this black hole, this big black hole starts moving to the boundary of ADS. You focus on a little patch of it, and that little patch looks like a planar black hole, what we sometimes call the Poincare patch black brane. Looks like a black brane living in Poincare patch ADS. Okay, so this black hole, which initially had spherical symmetry, now this little patch of that turns into something that has translational invariance, becomes planar. And sorry, was there a question? No. Okay, great. This becomes planar, and instead of expanding modes in spherical harmonics, you can now expand modes in momentum eigenstates. Okay. In particular, if you compute the quasi-normal modes, if you compute the quasi-normal modes of this black hole in this limit in which it's become a plane, the spectrum of quasi-normal modes is parametrized by a momentum rather than angular momentum. Okay. And when you study the spectrum of quasi-normal modes of these black holes, you find something interesting. Okay, so you can take these quasi-normal modes and fix the spatial momentum of these modes. Okay, and then you can try to find the energy of these modes, the frequency of these modes, time frequency of these modes, as a function of the spatial momentum. Now there are several quasi-normal modes. But when you solve this problem, you find something interesting. The interesting thing you find is that while in general at any fixed k there are an infinite number of quasi-normal modes, and all of these modes are very massive. They have masses of order the temperature of the black brane, or the radius, the event horizon radius of the black brane. You find that there are a few modes, in fact d-1 modes, which become almost massless, whose frequencies go to 0 in the limit that k goes to 0. Okay, so you look at the quasi-normal modes as a function of spatial momentum. Take the limit k goes to 0. At any k, including in the limit k goes to 0, there's an infinite number of quasi-normal modes. Most of these are massive, but there are d-1 massless modes in the limit k goes to 0. D-1 modes whose frequency omega goes to 0, in the limit spatial k goes to 0. Okay, so we're in a situation where we've got a few light modes, these few massless sort of modes, separated by a gap from an infinite number of very, very many heavy modes. Okay, more or less every time this situation arises in physics, one can find an effective nonlinear problem for the light modes by integrating out the heavy modes. Okay, so to speak. Now, in this paper written long ago now, 15 years ago, we were able to do this problem. We were able to accomplish this. We were able to integrate out the heavy modes and find the effective nonlinear theory of the light modes. And the result we got was very interesting. The effective nonlinear theory of the light modes was governed by a set of differential equations for fields that lived in d-1 rather than d dimensions. And the differential equations that we found were the equations of hydrodynamics, the equations of a conservation of the stress tensor, where the stress tensor was given by a particular functional of the velocity fields and the temperature, the local velocity fields and local temperature fields on this vibrating sort of black brane. Okay, so not only were we able to find the effective nonlinear theory of these light quasi-normal modes, the theory turned out to be something, not some nonsense, turned out to be familiar equations, the equations of hydrodynamics. Okay, now let me emphasize a few points. Our effective hydrodynamical equations are standard hydrodynamical equations, and therefore presumably define a well-posed initial value problem. In particular, note that we've got as many equations as variables. The number of equations here is the number of space-time dimensions. The number of variables is also the number of space-time dimensions, because we've got d-1 velocities and a temperature. Okay, so in this limit, black hole dynamics reduces to another problem, which is not a trivial problem. It's a problem of hydrodynamics, but another problem, a problem that is non-trivial but does not involve gravity, a non-gravitational problem. Okay, this this map between the equations of gravity in these asymptotically area spaces and this effectively hydrodynamical problem, non-gravitational, non-linear, interesting hydrodynamical problems, sometimes called the fluid gravity correspondence. Okay, and it came from, as I reviewed, basically trying to find the nonlinear theory of the light of a set of light modes separated from a gap from an infinite number of very heavy modes. Okay, now you might have thought that it's sort of incredible, right, that we study a gravitational problem. We find some effective description of the equations of motion of this black hole, and these effective equations are not some new strange beast, but a formalism that has been studied for 200 years, namely hydrodynamics. And of course, at first you might have thought that this was luck, but of course it's not luck. It's explained by the ADS-CFT correspondence. Okay, and this connection proved very useful. It initiated a program to better understand the equations of hydrodynamics, which over the last 15 years has yielded many results. Okay, great. So far so good. All I've done so far is review for you the old story of the connection between gravity and fluid dynamics.
Ross, could I ask a question? How important is the planar limit for this story? Can it be just a small black hole in ADS and you still get such an effective description?
No. It wouldn't work if it was a small black hole in ADS. The equations that we got here were equations in an expansion in derivatives divided by temperature. Okay, so if we had a black hole of a certain size, a size whose like spherical size was of order the temperature, then there would be no modes for whom the derivative was smaller than the temperature. Right? So what we got, so I should have emphasized this, what we were able to do was to derive these equations in a systematic expansion, which is long wavelength expansion. And for this long wavelength expansion to make sense, it was necessary that this black hole at least have size that was sort of much larger, sort of curvature radius that was much larger than the length scale on which this derivative expansion was being done, which was sort of the temperature. Is that clear?
Yes, that's clear.
Okay, great. Okay, so I've reviewed the story to give you motivation for the newer expansion I'm going to talk about, namely the expansion in a large number of dimensions. So one could ask, could something like fluid gravity work for Schwarzschild black holes in flat four-dimensional spacetime? Could it be that the equations of nonlinear oscillations around the black hole reduce to something like the equations of hydrodynamics on some three-dimensional spatial slice? And if you ask this question, the first response that occurs to you is surely not. Okay, and the reason for this is that, well, such a theory, if it exists, presumably very, very similar to the answer I just gave, Dan, presumably lives on a sphere whose radius is of order RH. Its modes would thus have frequencies of order 1 over RH, which is the only length scale in the theory. But this is the same as the scale for the energy gap between quasi-normal modes, which again is set by 1 over RH, because that's the only length scale in the theory. So there can be no decoupling. You never have a situation where you have some modes parametrically decoupled from other modes. Okay, and this intuitive argument is correct and can be checked by computations of spectrum of quasi-normal modes and their couplings and so on. None of this is very surprising. It's usual thing we learn that you've got an intractable problem, unless you're very lucky. A simplification usually requires a parameter. Here we had a problem without a parameter, so there was no simplification. Okay. Now, in the rest of the talk, I'm going to try to introduce a parameter to the problem by studying black holes not in d equals 3 or d equals 4, but studying black holes in all dimensions and using 1 over d as the parameter. Okay. So to set up that problem, consider a d-dimensional Schwarzschild black hole boosted to velocity u mu in Kerr-Shield coordinates. Okay. The metric for such a black hole, if you're not familiar with Kerr-Shield coordinates, takes a slightly unfamiliar form. It's given by the metric of flat space plus a correction term. Okay, this correction term involves this boost velocity, which is just some constant, squares to minus 1, and involves this function r, where r is just space, the magnitude of space in the direction orthogonal to the boost velocity. Okay, so mathematically, r square is defined by this quantity, where the PMN is the projector in flat space orthogonal to u. Okay, so if you were sitting in the frame where the black hole was at rest, r would just be the radial coordinate in space. Okay, so this is the usual Schwarzschild black hole metric in perhaps some slightly unfamiliar coordinate system. Now, maybe 10 years ago now, or 9 years ago now, Emperor, Suzuki, and Tanabe made the following simple but very important observation. They looked at this metric, and the first observation was that in the limit that d goes to infinity, if you take r by r naught fixed to any number that is larger than 1, and then take d to infinity, this term here goes to infinity, and therefore the metric just becomes eta mn plus 0. And so it becomes a metric of flat space. Okay, so this is the first observation, that in the limit, if you take r by r naught to infinity fixed and take d to infinity, the black hole metric anywhere outside the event horizon, if you stay fixed as you take d goes to infinity, just becomes flat. Okay. This reflects the fact that Newton's law falls off very rapidly in a large number of dimensions. The second observation they made was this: that instead of holding r by r naught fixed as we take d to infinity, if we let r equals r naught into 1 plus capital R divided by d minus 3, therefore we let r by r naught be 1 up to a deviation which is r divided by d minus 3. So r divided by d, roughly speaking. Okay, and then we take the limit d goes to infinity. Then by using familiar formula, this limit turns this quantity into the exponential of minus r. So now the metric is no longer just that of flat space. It deviates from flat space, but deviates from flat space in the coordinate r, which, recall, was when r was order 1, the physical coordinate r, the distance coordinate r, little r, was different from the event horizon at order r divided by d. Okay, so physically, Emperor, Suzuki, and Tanabe observed that the black hole has a little shell of spacetime whose of thickness order event horizon divided by d, over which its metric deviates from that of flat space. After that, for coordinates larger than that, the metric just becomes flat, that of flat space.
Shiraz,
Okay?
so
Yes.
the Coulomb field falls off very fast in higher dimensions, but the centrifugal piece in Kerr probably doesn't, right? That's usually always like 1 over r squared. Does this decoupling also work for a spinning black hole?
Yes. It does also work for spinning black holes, and in fact, one of the things that we've done in this program is to produce spinning black holes as spinning membrane solutions. The point is that this decoupling works sort of locally, and if you just move a little distance in some direction here, that decoupling happens sort of automatically. I will have some formulas for this as we go on.
Okay,
may make it a bit clearer. Okay. Yes. Just to say it again, the centrifugal force that you're talking about, of course, is true, but it's accounted for by the membrane equations. It's a centrifugal force for the membrane. So that's taken into account by what we do. Okay. This may become clearer as we go on, and please ask again if it's not. Yes. Okay, great. So now let me say again, the key point here is that there are 2 different length scales in the problem at large d. The first is the length scale of the event horizon. Okay, and the second is the thickness outside the event horizon where we see the field, the thickness of the event horizon, roughly speaking. I mean, not of the event horizon, but the thickness of the region outside of it, the distance away from the event horizon that you have to go before you stop seeing that there's a black hole at all. And that's of order R naught divided by D. And you might ask, does this second length scale show up in dynamically interesting quantities? Now, Emperan, Suzuki, and Tanabe answered this question by computing the spectrum of quasi-normal modes around a Schwarzschild black hole. And just by doing the calculation, they found that the spectrum of quasi-normal modes had an interesting structure. Okay, in this case, the spectrum of quasi-normal modes is organized by angular momentum. Every angular momentum, there was an infinite number of heavy modes where the frequency of these modes was of order d divided by r naught. But at every angular momentum, there was also a finite number of light modes, okay, with frequencies order 1 divided by r naught. Okay, and this was an interesting and very key observation, because it suggested that the situation was like that in fluid gravity. We've got these few light modes, many heavy modes. You should be able to somehow integrate out the heavy modes to make a nonlinear theory of the light modes. Okay. Question, is this correct? Is it true that there is an interesting nonlinear theory of the light modes that you can find by integrating out the heavy modes? Is it hydrodynamic in nature? Is it interesting? With a few caveats, the answer, in my opinion, is yes, yes, and yes. And I'm going to tell you about that. Now, you remember we started with this black hole metric here, which was just the metric of the Schwarzschild black hole, okay, where U was some constant velocity field and R was a specific function. Now consider this more general metric, okay, this more general metric, which at this stage I'm just writing down by hand, where the metric is the metric of flat space plus any function in flat space, and then n is the normal to constant rho surfaces. So n is given by d rho divided by square root of d rho squared by rho squared, where all these contractions are done in the metric eta m in flat space. Okay, U squared is any one-form field in flat space. It squares to -1. Again, that squaring is done with a flat space metric. And we also require that U dot n is equal to 0. This was true of the black hole, the special black hole, Schwarzschild black hole metric that we were familiar with. And this property we demand continues for this at the moment very fluffy, very unconstrained class of metrics that we just write down. Now, so far, metric obeys no interesting equations. But already there are one or two things that are sort of nice about this metric. The first thing about this metric is that, just as we saw in the case of black holes, this metric is flat when rho minus 1 is much, much greater than 1 by d. It's the same mathematics that we reviewed about that r divided by r naught to the power d minus 3. Okay, so if the places where in space where this rho is larger than 1, where its largeness is 1 by d or larger, much larger than 1 by d, this metric reduces to flat space. So this metric is if we consider some rho function which is larger than 1 in some region, but is less than 1 in some region and then becomes larger than 1 outside it. In the region where rho is larger than 1, this metric is just flat. It's an asymptotically flat metric. Now, you see from this point that rho equals 1 is somehow a special place in this metric. Okay, I'm going to call the submanifold of the spacetime where rho is equal to 1, I'm going to give it a name. I'm going to call it the membrane. Now, one thing that's special about the submanifold rho equals 1 is that the submanifold is a null manifold of this metric. This is very easy to see. It's easy to see just by computing the norm of the normal to rho at any general value of rho in this metric. The normal vector, the norm turns out to be 1 minus 1 by rho to the power d minus 3. This is a 2-line calculation. And when rho is equal to 1, this goes to 0. So rho equals 1 is a null submanifold of the metric here. And the generators of this null submanifold, the tangents of these generators are in the direction of u mu. This is another easy thing to check. Okay, so far we've just written down some metric. Now, we're not just interested in writing down some metrics, we want solutions to Einstein's equations. The sort of remarkable fact that we established is the following. If we choose this function rho, not to be completely arbitrary, but to be a harmonic function, to obey the equation del squared 1 over rho to the power d minus 3 is equal to 0, and provided the shape of the rho equals 1 surface and the velocity field here, this one form field restricted to the rho equals 1 surface, obey a set of equations of motion, which I'll tell you about in a minute, then the metric here is not just any old metric, but it's a metric that is a solution to Einstein's equations at 0th order and can be systematically corrected in a 1 by d expansion, in a systematic expansion in 1 over d to a true solution to Einstein's equations at every order in 1 over d. Okay, I told you that this is true provided this velocity field on the membrane, on the surface rho equals 1 on the membrane, and the shape of the membrane together obey a certain set of equations. I'm now going to tell you what these equations are. Okay, the equations that these fields are forced to obey take a sort of elegant form. They take the form of a set of conservation equations for a stress tensor living on a submanifold of flat space. So the stress tensor actually lives in all of flat space, but because the stress tensor has a delta function, this delta function is localized at rho equals 1, so the stress tensor is non-vanishing only on the membrane submanifold. Okay, so it's proportional to a delta function times something, and the something, whatever it is, I'll tell you more about what it is, has the property that it's, when dotted with the normal to the surface rho equals 1, it vanishes. Now, because this stress tensor then is dotted with the normal of this manifold is 0, the stress tensor descends without losing any information to a stress tensor on the world volume of the membrane. Okay, and in the rest of this talk I will talk not so much about the space-time stress tensor, that will come back once in a while, but the stress tensor on the world volume of the membrane. So that's what I've called T mu nu. Now, it turns out that this T mu nu here takes the following form. T mu nu is the sum of a fluid stress tensor and what we call a total derivative stress tensor. Okay. The total derivative stress tensor takes the form K mu nu minus G mu nu K by 2, where K mu nu is just the extrinsic curvature of our surface and K is the trace of that extrinsic curvature. The fluid stress tensor, on the other hand, takes the following form. It's given by kappa tilde times the projector orthogonal to the membrane velocity u mu minus a shear tensor. The shear tensor is given by this structure, and kappa tilde is defined in terms of extrinsic curvatures by this structure. Okay, it looks a bit complicated. But I'll unpackage parts of it for you as we go on. Okay. Now, I told you that we had the stress tensor on the world volume of the membrane rho equals 1. Okay, and I told you that our equations of motion were conservation of the stress tensor. The conservation of the stress tensor gives you d equations because there's d free indices, this index A. However, it turns out that if you take the part of the conservation of the stress tensor and dot it with the normal to the membrane, that term with the form of the stress tensor here is identically 0. So actually, conservation of the stress tensor is only d minus 1 equations, and those d minus 1 equations are simply world volume conservation of this world volume stress tensor T mu nu. Okay, so now we know the number of equations we have. The number of equations we have is d minus 1. But the number of variables that we had in our problem is also d minus 1. Okay, the number of variables is also d minus 1 because we had one shape variable. That's the shape of our membrane. That's one variable, and we had a velocity variable that was living on a d-1 dimensional surface. Since velocity squares to -1, that's d-2 variable. So d-2 plus 1 is d-1. So the total number of variables in this equation is d-1. The total number of equations is also d-1. Okay. Now, the full equation is the equations can be thought of as a conservation of this world volume stress tensor. I told you the world volume stress tensor was the sum of this fluid part and this total derivative part. The reason we call this a total derivative part is that the total derivative part is identically conserved. This is something easy to see. So
is that just the Brown-York stress tensor?
Yes, it's just the Brown-York stress tensor, and the conservation is that of the Brown-York stress tensor. Exactly. Okay. So the non-trivial statement of conservation, you see, even though the stress tensor here, this total derivative part didn't contribute to equations of motion, it will contribute to sourcing gravitational radiation. So it's sort of not completely, not there. But okay, the non-trivial part, as far as the equations of motion are concerned, is simply the fluid stress tensor, and so the equations of motion, the dynamical equations of motion, are that this fluid stress tensor that lives on this world volume of membrane is conserved. Okay, so as I said before, we had d-1 non-trivial membrane equations, and that matches the number of variables, d-2 velocities and a shape. Now the equations that we have in this membrane are essentially those of hydrodynamics. Okay, we have the same number of variables as equations, and so hopefully this defines a well-posed initial value problem. This has never been seriously studied. Even establishing that relativistic hydrodynamics is a well-posed initial value problem is a topic of research, and this has never been seriously established. That's something I'd love to know for sure. Okay, notice that the equations that we have are basically those of hydrodynamics on a wobbling membrane. Though there's one novel feature. Hydrodynamics, as we reviewed in the first part of this talk, usually hydrodynamics has two kinds of variables. There's a velocity field and an energy density field. Okay. Now, if you put hydrodynamics on a wobbly shape, you would imagine that the total number of variables was d plus 1. Namely, you would imagine that the total number of the variables that it was d. Namely, that you would imagine that there would be a velocity field, an energy density field, and a shape. Turns out that this membrane here does not have an independent energy density field variable, a temperature variable. Its only variables are that of a velocity and its shape. This is somehow related to the fact that in black hole physics, the shape of the black hole determines its temperature by the extrinsic curvature. Okay, so it's a sort of novel kind of fluid, one which has a velocity field but not an energy density field, but it also has a shape, the shape of the surface on which it's living. Okay, a little more about these equations of motion. If you take the conservation of the stress tensor and you take the part of it that is in the direction of the velocity, dot that conservation with the velocity, you find the equation becomes del dot u is equal to 2 by kappa times this shear square. Now, let us define this quantity, u mu by 4, as an entropy current. Okay, I'll tell you in a minute why that's justified. Making that definition, this equation becomes the divergence of the entropy current is a positive definite object, okay, which is shear squared divided by something. Now, why did I identify this J mu s with the entropy current? This J mu s, by using this map between something I should have emphasized is, for every solution of the membrane equations, we have a solution of Einstein gravity. You may have it, written down, right? It's explicit metric. Now, the solution of Einstein gravity has an event horizon, and that event horizon has its usual area form, the Hawking area form that gives you the entropy current, that gives you an entropy form on the event horizon of the black hole. Okay, this quantity here is precisely that entropy form. Okay, it's sort of like the pullback of that entropy form onto the world volume of this membrane. Okay, so it really is the entropy of the black hole that this membrane is dual to. And in fact, this statement here is simply the membrane dual of the Hawking area increase theorem, that the entropy locally on a black hole horizon always increases and never decreases. Okay, so hydrodynamics like every good hydrodynamic is equipped with the positive divergence entropy current, local positive divergence entropy current. Right. Now we've got this membrane and this black hole, and it's wiggling around. And you might think, well, if the black hole wiggles around, it should be radiating. Okay. And the answer is yes, it is. It is. As it wiggles around, it's radiating. But the next question you might have is, well, if this black hole is radiating, how come we've got autonomous local equations just on the membrane? Because, there should be radiation here, which then goes and travels to this part and affects that part. It doesn't sound right that you can have radiation together with autonomous decoupled local dynamics. So in order to answer this question, we worked out in great detail the details of the radiation of this problem. The philosophy was very simple. You see, I've told you that we were able to construct these metrics dual to any given solution of the membrane equations. Now, the solutions that we were able to construct, I haven't told you the technical details, but we were able to do it systematically, but in this region, in the region where rho minus 1 was much less than 1. Up to that region, we were able to construct these solutions. And then for larger than that, we didn't really care, because by then the solution had exponentially decayed to very near flat space. Okay, but as I just said, the solution exponentially decays to very near flat space, and the length scale for that decay is 1 over d. So you see, where we could construct our solutions, there was a region where the solutions were highly nonlinear. But there was also a region where we could reliably construct our solutions and it overlapped with linearized gravity. Okay? Now, the solutions of linearized gravity then can be continued just by solving linearized gravity all the way to infinity. So by working through this procedure, we were able to determine the radiation fields of any given membrane solution. And the answer turned out to be satisfyingly simple. The answer turned out to be that the radiation is precisely the radiation that one would get by taking a membrane moving in flat space with the stress tensor that we have here, and coupling that to Einstein's equations at linearized order. Okay, so the radiation is given just by the membrane stress tensor. So not just the motion of the membrane, but also the radiation is created by the black hole solutions, is accurately captured by the membrane stress tensor. Now, what's the answer to our puzzle? Turns out that's a kinematical fact in large D, having to do with Green's functions in large D. Okay, that radiation fields from energy densities of order 1 decay are very, very small. They're of order 1 over d to the power d. Okay, and this is minuscule. It's even smaller than exponential in large D. And this explains why radiation could occur without inhibiting our ability to compute the local dynamics of the membrane to every order in 1 over d, because this was just a very small correction. Okay, great. Fine. So generalizations. All of the story that I've described was worked out for Einstein gravity, but has been repeated for Einstein Gauss-Bonnet gravity. Actually, a set of very interesting papers that I feel should be taken further by these authors. Okay. In addition, I started with Einstein gravity in flat space, but the story has been extended to include Einstein gravity in spaces with cosmological constants, positive and negative, in these papers. It's been repeated for Einstein-Maxwell theory, so including charge as well. That's an interesting story, because now a membrane becomes, the variables on the membrane become its shape, velocity, and a charge density. So it becomes charge fluid dynamics. Okay, here. And in this paper, we demonstrated that though explicit results for these membrane stress tensors and so on are only to first a second subleading order and 1 over d, we demonstrated that the procedure formally carries over to all orders in 1 over d.
Shiraz?
Okay. Yes.
Can I ask a question? So if you introduce charge, you introduce also the possibility of making the membrane extremal in some way, I would guess.
Okay, yes. That allows for that possibility, but precisely where the membrane goes extremal, these methods start failing. It's actually very similar to similar situation that arises in fluid gravity. let me give you a technical, well, there is a technical and a physical way of saying this. The technical way of saying, maybe I should give you the physical way of saying it. The physical way of saying it is this, that you see, what was important for us is that the distance between our point, any point that we were looking at, and the event horizon was a finite distance. Okay, as the black hole starts going extremal, we develop this ADS2 throat near the horizon, and in the limit that the black hole is really extremal, that thing there has an infinite throat. Okay, because of that, there are many new light modes that start coming down. You see, the box here starts becoming bigger and bigger and bigger. And many of these modes that were heavy start becoming lighter and lighter and lighter, and eventually become sort of as light as the modes we're keeping. So in the strict extremal limit, none of this works. But this works to very near to extremality. In fact, in some sense, near to some order 1 over d to extremality, but not in the strict extremal limit. Sorry for the length of that answer. I hope it was clear.
Thank you.
Okay, excellent.
I have a slightly different question. Is there anything funny about the thermodynamics of these membranes? Because, like, for Schwarzschild, the formal density of states is usually super Hagedorn, and it's weird thermodynamics which you don't have in ADS.
Yeah. We reproduce the thermodynamics of these of Schwarzschild, but what's going on is this, that there is local thermo. Firstly, it's an excellent question. You see, it's a little like this. We're getting the thermodynamics of a solution. Now, suppose you had a balloon. Okay, you had a balloon with a surface tension, and you filled it with a hot gas. Okay, as you increased the size of the balloon, so the balloon would be in some sort of equilibrium, right? Because there would be like a surface tension of this of the balloon balancing the pressure difference between inside and outside. Okay. Now, as you increased the size of the balloon, this pressure difference would need to become smaller and smaller and smaller. Okay. So that tells you that smaller balloons have hotter stuff inside, right? Because let's say there's certain pressure outside, the pressure inside needs to be even more in order to balance this curvature, which is larger, of the surface tension. Whereas as you increased the size of the balloon, the hot stuff would have to have lower pressure and therefore have to have lower temperature. So this kind of balloon has negative specific heat. Okay, and I would have to think about super Hagedorn, but would have if you just looked at its thermodynamics by itself, would look very funny. For instance, it would have negative specific heat. Okay, but you see that this is coming about from putting together standard things like an elasticity standard equation of state of the gas inside, and so on. So often it happens that finite systems made of very standard material, if you look at the thermodynamics of the whole gadget, sort of looks funny. And I think that's what's going on in this membrane. Was that clear?
Yes. No, yeah, okay. That was great. Nice.
Okay, thank you. Okay, great. Okay. Now, I was going to spend the next two transparencies talking about connections with what other approaches to this problem, but in view of time, I'm going to skip this, except to point out that there's this really interesting paper by Emperan and Suzuki 3 years ago, which in a very particular context deals with this membrane at length scales smaller than our expansion is able to deal with. At length scales of order, where the membrane fluctuates not at distances of order 1, but at order 1 over square root d and 1 over d. And was trying to study this Gregory-Laflamme problem and thin tubes. What I've said in the part that I'm skipping is that most of the other approaches to this problem are subsumed in our general equations, a special case of our general equations. That's not true of this this paper. I don't think much has been done with it since, and I think it's a very interesting paper. I feel, I'd like to flag it because I think it's very interesting. But apart from that, I'm going to move on. Okay, now, so far we've found these general, so far what we've done is found these general equations. Now let's look at some solutions of these equations. Okay, first thing we're going to do is to try to find stationary solutions to these equations. Okay, now if we want to look for stationary solutions, this is coming to relating to a question Dan had asked at the beginning. I'll come back to right. So we're looking for stationary solutions to these equations. Now, what we want to do is to find stationary solutions of our membrane equations. Now, we want stationary solutions. We want solutions in which the entropy current is divergence vanishes, because entropy shouldn't be being created in these solutions. It should just be stationary. So del dot J should be equal to 0. But del dot J in our problem was just del dot U. So del dot U must be 0. But we see from this equation that del dot U is 0 only if the shear of the velocity field is 0. Okay? So stationary solutions are parameterized by a velocity that has both 0 divergence and 0 shear. Now, it's a simple theorem one can prove for oneself, that if you've got a velocity field in a space-time that has 0 divergence and 0 shear, then all such velocity fields are easy to classify, and in fact, this velocity field must be proportional to a time-like killing vector in the space-time. So if we want stationary solutions, the velocity field has to be proportional to a time-like killing vector. Let this time-like killing vector be k mu. So k mu could be d by dt, and then we would get, in what I'm saying, we would get the Schwarzschild solution, or it could be d by dt plus d by d phi, and then we would get a Kerr-type solution. Okay. So this velocity field has to be, u mu is equal to k mu divided by its norm, so that it's a velocity field. Wonderful. So, the hard part in solving these membrane equations was to find this velocity field and find the shape. There were d-2 velocity fields and one shape, and just in one shot, using one equation, we found the d-2 velocity fields. Now we're left with d-2 equations to find the shape. And you might think, okay, now we're in trouble because it looks like there won't be solutions to these equations, because we've got d-2 equations for one variable. However, of course, everything is good and there are solutions. It turns out that these remaining d-2 equations turned out all to be the derivative of a single equation. Okay, and so all these equations are obeyed when this is a constant, and that constant I choose to call 4 pi by t naught. Soon we will identify t naught with the temperature of the solution. Okay, so when kappa tilde is 4 pi by t naught divided by square root of minus k dot k, all our membrane equations are obeyed, and this gives us stationary membranes. Okay, now we and others have studied these solutions. When you have these rotations, these membranes bulge out into these ellipsoids. That's the centrifugal force that Dan was talking about. You see, that's all accounted for by the membranes. Okay, so in summary, stationarity requires these conditions, and you can sort of easily solve membrane equations in these limits. Okay, next question. We've got these nice stationary solutions. Okay, next question. Can we get our membrane equations out of an action? The answer to this question in general is no. I mean, no in an easy sense. Because you see, our membrane equations are equations of hydrodynamics and dissipative. Entropy production is happening in these equations. And typically one cannot get equations which are dissipative out of an action in a simple way. Maybe by doubling degrees of freedom, the Schwinger-Keldysh contours and all of that, but in a simple way, we cannot get, it's difficult to get dissipative equations out of an action. However, if we focus on the stationary limit, then there's no dissipation happening. So one might hope that it's possible not to get the general membrane equations, but to get these equations. Okay, the stationary equations out of an action. Turns out that's possible. You can write down the following action, which is the integral of the extrinsic curvature on the surface of the membrane, times the integral of the sort of the area of the membrane weighted by this killing vector. Remember, stationary solutions exist only when there's a killing vector. It's an action involving a killing vector. And if you have a cosmological constant, also the integral of the volume of space-time enclosed by this membrane. Okay, this action is an action whose variation one can show reproduces these stationarity equations. And moreover, if you vary the action with respect to the metric on the world volume of the membrane, and you have to think a little bit for what this means. But once you give that a clear definition, you produce a stress tensor by this formula that agrees with the membrane stress tensor, the general membrane stress tensor I told you about before, when restricted to stationary solutions. Moreover, this action has a very clear thermodynamical interpretation. Okay, turns out that our action can be. You can show that our action is equal to beta times E minus T naught times the entropy. Okay, where beta times E minus T naught times the entropy, where E is the energy of our membrane and S is the entropy, and beta is 1 over T naught, and T naught is the parameter that enters here. But because of this identification, can also be thought of as the temperature of our solution. Okay, so we've got a very beautiful thermodynamical interpretation of. So notice that this action played one role. It is the thing that generated, whose variation generated equations of motion, generated the equations that told you what your stationary solutions were. But it has another role. It's got a thermodynamical role. And from this thermodynamical point of view, the action is simply the entropy, because the T naught cancels between this beta and T naught. Sorry for writing it so badly. The entropy, okay, at fixed energy. Fixed energy is being enforced by this Lagrange multiplier T naught. So basically, the equations of motion that determine stationarity are the equations of motion that follow from the requirement that entropy is extremized at a fixed energy, which is, of course, very satisfactory, given that's how you expect thermodynamics things to behave, thermal objects to behave, right? I mean, you fix the energy and that it should find its maximum entropy configuration, and that's exactly what this membrane does, as this action shows. Okay, now I've told you about how stationarity works at formal level. Let's ask how it works practically. So suppose can we practically find solutions to these stationary equations? Well, the simplest such solutions are just stationary solutions, right? I mean, static solutions, like Schwarzschild black hole in flat space, or ADS Schwarzschild black hole in ADS space is the corresponding thing in de Sitter space. Okay, well, in that context, it's easy. It's easy to look for solutions to these membrane equations, either in flat space or in ADS space or in de Sitter space, and then compute the mass and the temperature, and therefore the entropy, and therefore the thermodynamics of these solutions. And we find a bit of a surprise. When we do that, our membrane reproduces the entropy of the thermodynamics of black holes exactly, even at finite d, even though there was no reason for this to happen. Just turns out that that when we work out all the details, you get the exact answer for the for black hole mass, black hole temperature, the black hole thermodynamics from this membrane. It was sort of cool. Okay, now that we have this, we could ask for how you can map this story to the story of fluid dynamics. So what do I mean by that? Fluid gravity. What do I mean by that? Consider now an ADS space in large D. Okay, so ADS and the long wavelength limit gave rise to this fluid gravity correspondence. Very nice. Now suppose we take ADS at large D, and we've got a membrane moving around in this ADS space. This membrane can move around in any way, any old way, obeying our membrane equations. But if we demand that it's sort of more or less like a planar membrane with some small ripples, one can solve the membrane equations and then take the radiation from this membrane equation, push it to the boundary, find the stress tensor on the boundary of ADS, and check what the equations of the motion of the membrane translate into equations of motion for the boundary stress tensor. And it will not surprise you that if we do this, we find that the boundary stress tensor precisely obeys the equations of relativistic hydrodynamics with the constitutive relations that we got from fluid gravity. But once again, there's a surprise. I'm not sure surprise, but once again, something nice, which is that the constitutive relations to first order and the derivative expansion work out exactly right, even at finite d, even though that was not guaranteed to happen. Though from second order onwards, the constitutive relations that we get from this procedure only are correct at large d, but they have 1 over d corrections. Okay. Another calculation we tried was the following. We computed the quasi-normal mode frequencies of a charged black hole at large d, starting with our membrane. This is the result we found. And Emperan, Suzuki, and Tanabe had directly computed it starting from gravity. And of course, these results, the light modes match. That had to be okay, right? Because the light modes, we made our membrane theory is a nonlinear theory of these light modes. Surely should reproduce the linearized light modes. This is just a check that it works. Okay. So one last thing about this hydrodynamics, something I've always found interesting, but you've never made progress on, at least not yet, is the following. There's this long-standing question about whether hydrodynamic equations develop singularities in finite time. And to the best of my understanding, this question is, genuinely unsolved in the sense that people really don't know whether this happens or not. Now, I want to say that in this large D context, this membrane gives a new perspective to this problem, in my opinion. You see, because suppose you've got a membrane here, and it's moving like this. Now, suppose I take a bit of the membrane that's on top of the other part of the membrane and give it a faster velocity than this guy. Then you can imagine that the membrane undergoes a sort of fold. From the point of view of the fluid gravity variables would be a singularity, because fluid gravity requires the black hole horizon to map to the boundary in a one-to-one way. On the other hand, from the point of view of the membrane equation, it's not singular at all, because the membrane is much more flexible than fluid gravity. As long as its local curvature is small, it can take whatever shape it wants. So I think that there's a chance that in this context, what one would see is that you would get an apparent singularity for the hydrodynamic equations, the fluid gravity equations. But that the singularity was just an apparent singularity. And if you change to the right variables, which in this case would be the local shape of the membrane, that singularity would go away. You just realize that you were using the wrong variables. You have to use, multi-sheeted variables. And then the whole thing is non-singular. So all this there are no equations to back what I've said now. It's just some words. But somehow I find it interesting, and I wonder whether that can be taken forward. Okay, so let me stop with a summary. What have we done in this talk? What I did was to reformulate black hole dynamics in large D. The reformulation was sort of nice, in my opinion. The effective equations were a set of non-gravitational equations for a sort of soap bubble, moving in flat space, or in ADA space if that's where you started working. The variables of that soap bubble were velocity of the stuff that it's made of and the shape of the bubble. There were some very definite equations of motion. The equations of motion came out of Einstein's equations. They were derived from Einstein's equations. These equations of motion were derived at first to leading order in large D, but we've also found the first subleading corrections, and we've shown that there's no barrier to carrying out this expansion to arbitrary orders in 1 by D. As the membrane moves around, it radiates. Radiation is suppressed at order 1 over D to the power D. The fact that it's so small is essential for the consistency of this picture. It's sort of like a Mulder-Sena limit for Schwarzschild black holes. Remarkable, isn't it? Except that it only works at large D. Okay. Stationary solutions are particularly simple. Velocity fields are proportional to Killing vectors. There's a simple equation for shape. Such solutions are obtained from extremization of a simple action. The action has a direct thermodynamic interpretation. It's the on-shell partition function, obeys all the laws of thermodynamics. We should check this explicitly. Okay, and one other nice thing is that some of the results that we got, some of the more simple results we got out of these membranes, by direct calculations, matched gravity better than it needed to. Some things worked even at finite D. Now, what might all this be good for? I don't really know. I've told you everything I know about this program, but I'm going to give you 3 speculations, then I'll stop. The first thing it might be good for is as an approximation scheme for motion of black holes in 4 dimensions. You know, at first, this may sound absurd to you, but 1 over n was pretty good approximation for aspects of QCD physics, even though n was 3. So maybe this could give us some insight for motion of black holes even in 4 dimensions. Okay. Usually speaking, theoretically nice objects have uses that are not of this sort. My guess is that the most interesting results of this program, if they fructify, will be structural. Okay. Something I've tried hard with my student Shuman, who's on this call, I think. We never managed to succeed, but maybe one day we will, is to try to improve these membrane equations so that they correctly reproduce. Something I didn't tell you about was this. I told you that static solutions of these membrane equations reproduce static solutions of Einstein's gravity exactly even at finite d. You could ask, does the same thing happen for stationary solutions? The Kerr kind of solutions that Dan was asking about at some point. And there, unfortunately, the answer is no. You compute these things and they agree, of course, as they should at large d, but they have 1 over d corrections. So something that I've tried hard, and I somehow feel is possible, I've not managed to find it, is to find an improved set of membrane equations that works exactly for all stationary solutions, even at finite d, and then works for dynamical solutions only order by order 1 by d. I think this might be possible because anything more than that is impossible. For dynamics to work exactly at 4D in some local membrane way is impossible because there will be radiation, and radiation is non-local. Okay, so for dynamical situations, I don't think we can do better than we have done. But for stationary solutions, there's no radiation. So it feels like this approach one should be able to make this approach exact at stationarity, but 1 over d exact, 1 over d approximate for dynamics. And the fact that static solutions work out bang on exactly at large d gives hope, but we've never managed to find this improvement. Now, the last point, and then I'll shut up, is the following. This, I think, is the most interesting possible application. And Arunabha Saha, our ex-postdoc, has worked on it, and maybe he's making progress on it, is the following. Over the last 15 years, we've learned a great deal about the structure of the equations of hydrodynamics. And one of the things we've learned is that if I give you an arbitrary set of hydrodynamical equations, they're not consistent in the sense that they do not. If I give you just any old hydrodynamic equations, in general, you don't have these equations aren't equipped with the positive divergence and entropy current, which is something that is needed for hydrodynamics to make sense. Okay. Now, what we've done here is to work out this membrane hydrodynamics of the membranes dual to black holes and Einstein gravity. There's this interesting question that many people, including Shantanu Bhattacharya and Aaron Wall and others, have been looking at, which is the question of whether there exists a second law for black hole thermodynamics for higher derivative corrected gravity. Some people suspect that the answer to that question is no. I'm one of them. And one way we might be able to prove that is to sort of show that these membrane equations are inconsistent for any higher derivative corrected gravity theory, except Einstein gravity. I've had some vague thoughts about this, but again, no clear results. Sorry for the vagueness of this ending. That's it. Thank you.
All right, thank you, Shiraz, for the fantastic talk. We have time for questions if anybody would like to go. Well, maybe I'll get it started then. This is kind of a vague question, but I'm just curious. I mean, there is like a very old and pretty big book called The Membrane Paradigm, where people like Thorne basically showed that, even low dimensional black holes behave in some sense like a membrane. It seems like you've found the limit that really makes that precise, but could you explain what the actual relation is? Is it that?
Yeah, well, the actual relation is, what these guys do, to the extent that I've been able to understand it, is take the Einstein constraint equations on the horizon and reinterpret those equations in terms of in terms of velocities and shears and things like that, fluid dynamical kinds of things. Okay, the new element in what we've done is that we have used large D to solve for the metric. Okay, to solve for the metric. So actually something I did not tell you about, though I have some backup slides on it, but anyway, I won't subject you to that. Something I did not tell you about is how we got these membrane equations. So let me give you half a minute on that. You know, the way it worked is this. Large D enabled us to integrate the equations normal to the membrane to solve Einstein's equations. And then the membrane equations themselves came about from having constraints, from the constraint Einstein equations on the surface. Now, I said this because so we solve, if you take Einstein's equations and break them up, slice them along these constant rho surfaces, call equations that whose legs are in the rho direction, we call them constraint equations, whose legs are orthogonal, those are dynamical equations. Okay, I said that a bit wrong. Wait, Einstein equations where one of the legs has a normal factor. Normal to this metric is a constraint equation. But remember, yeah, and everything else is, we call that a dynamical equation. If you, and remember the normal itself is in the direction of the membrane, right? Because it's a null manifold, right? So if you do that, then you can solve the dynamical equations. And then after you solve the dynamical equations, these constraint equation becomes our membrane equations. Now, Damour and Thorne and so on also look at the constraint equations on the horizon. I think the difference is this. They have more variables than equations. Okay, their shear and their velocity are independent variables, for instance. Okay, so what they have is a set of constraints on data, but not an initial value problem. Because we were able to actually integrate these equations, we were able to relate these things that for them were different things, and get as many equations as variables, and so turn it into a proper initial value problem. So not a constraint on dynamics, but actual initial value problem, at least hopefully, at least initial value up to in the sense that as many equations as variables. Okay. To the extent that I've been able to understand the connection, this is it. Yes.
Do we have any other questions?
Shiraz, can you explain the significance of this point that this fluid, it's a fluid with no energy density? Can this be thought of as some extra symmetry or something?
Yeah, it's a great question. You know, the way it comes about, the way you could, right. Even in the Schwarzschild, you could ask this question sort of on the Schwarzschild black hole. You know, the energy density of this membrane, we say energy density, but sometimes in hydrodynamics, it's more useful to trade energy density for a temperature, a local temperature whose thermodynamics would give you this energy density. So we could ask, why isn't there an independent temperature variable and a shape variable? Okay, and you know that for a Schwarzschild black hole, once I know the size of the event horizon, I know its temperature. You know, so it's just a local version of that the curvature, local curvature of the horizon determines the temperature. This is how it comes about technically. Now, what it means, what kind of real condensed matter substance would have this, I don't know. It's sort of very interesting, right? That somehow the energy density is tied to its shape, and was key to this being consistent. This is one of this fact is one of the reasons that I feel that these systems may be much more constrained by consistency than ordinary hydrodynamics. You know, this fluid has to be consistent in a way that is consistent without having its own independent energy density, and there are couple of things that make it seem hard for this to be true. Let me tell you one of them. Look at this action here. Okay, the action here involved an extrinsic curvature. Okay, I also told you that the variation of the action with respect to the metric was a stress tensor. Now, I sort of pushed it under the carpet, but you could ask, what does this mean? What does it mean that the variation of this action with respect to the metric? Which metric? Is it the metric on the world volume? Is it the bulk metric? What metric are we talking about? Well, what we mean is the following. Okay, what we mean is the following. You're supposed to take this membrane surface and look at it in the space of solutions of Einstein's equations. Okay, in the stationary limit, you can argue that if you've got a stationary solution of Einstein's equation, and you know it's metric everywhere on the boundary, at least in some perturbation theory, you can argue that the metric on the boundary completely determines the metric inside. So if you know the metric of the world volume of the membrane, we know the metric everywhere inside as well. Therefore, we know the extrinsic curvature, because the extrinsic curvature is not just the metric on the world volume, it's a first derivative of it. Okay? But in general, the extrinsic curvature is an extremely non-locally determined function of the metric on the world volume. Right? I tell you the metric on the world volume, and you've won the extrinsic curvature everywhere. It's determined, but in a very non-local way. But precisely this combination of square root minus gk times this integral here is the combination of extrinsic curvatures and volumes whose variation is local on the membrane, giving rise to a local stress tensor. Okay, that follows from the fact that this is essentially the boundary term for Einstein's action, and this is the bulk term for Einstein's action in an ADS space. Okay, so somehow this whole story is very tight. Much of the action, I mean, is very, very fixed. There's not much room for variation. I'm sorry for the length of that answer, and I'm sorry for its incoherence if it was not yet.
No, that was great. Thank you.
All right, well, if there are no other questions, let's thank Shiraz again, and I'll stop the recording.